Yes, thanks. Welcome back. Let me take the opportunity to thank the organizers for inviting me to give these 4 lectures. I'll try to wrap up today sort of the algebraic part of the story and maybe some applications if we get to it. But quickly recall that yesterday we said, okay, I mean, we defined all these terms and we said if ever I want to calculate something and I care about only the homotopy groups or the homotopy type after I've inverted 2, I throw away 2 primary torsion information. The situation somehow simplifies, and this fiber sequence we constructed splits into 2 pieces, each of which I can understand, hopefully. And what comes out is I have to take the homotopy C2 fixed points on K theory and invert 2 on the outside, and then remember, now you're allowed to move the 1/2 inside, and then taking homotopy C2 fixed orbits is somehow something purely algebraic. Just calculate homotopy groups and then look at the effect of C2 on homotopy, and nothing group cohomological happening. Plus L theory of C copper adjoint 1/2. And in practice it is, in practice it's just that this term is easy to understand, and this term is how hard it is to understand. But I mean, the main game that we're trying to play is to reduce the whole complexity of Grothendieck Witt theory to the complexity of K theory. Sort of, we're not really going to make things much easier, except for accidents of the kind that you've seen that I claimed last time. That rationally, for instance, GW of the integers becomes easier because all the rational K theory classes are killed by the involution. Okay, so that's maybe something we have, and so it's a matter of fact. And we'll see an instance of this fact later. At prime 2, the fiber sequence, and okay, by this mysterious at prime 2, I mean if I'm interested in 2 local information or 2 complete information of GW, the fiber sequence KC HC2 to GW C copper to L of C copper, it suffers from the following symptom. So it's just a fact of life that the group homology of C2 is 2 torsion. And that, I mean, if you just calculate it on Z, yes, that's the homology of RP infinity, you find a lot of Z mod 2s. And if you do this kind of thing, I mean, in principle, the homotopy of this will be contributed by 2 torsion classes that really come from the group homology of C2. And it's a matter of fact that in L theory, there's just always also a lot of 2 torsion. And it's somehow an instance we'll see later that often the 2 torsion that's controlled by the orbits and the 2 torsion you see in L theory, they cancel. They don't add up. So somehow from this point of view, the fiber sequence is a bit annoying because you have to analyze the boundary map precisely and see that it does something, and the boundary map is only a derivation. Sort of algebraically, it's a bit annoying. It's not what you want to do. So the better thing to do, instead of looking at this fiber sequence, is something that Thomason suggested. And in, let me call it Thomason's HLP, the homotopy limit problem, because this is sort of a formalism in which he invented this stuff. In our world, it just means don't look at this fiber sequence. Instead, look at the map from Grothendieck Witt to the homotopy C2 fixed points. And you ask how well is it, how close is it to be a 2-adic equivalence? Just the better thing to do. Yeah. And we'll see instances of cases where this is correct, and sort of this fiber sequence has a lot of torsion here, a lot of torsion here, and they cancel out. And really, in this term, you don't see anything anymore. Okay, so that's the philosophy. But that tells us that we have to understand more seriously this map. And now, what's the first thing that we learn, which is a bit annoying, is that this map, on this side, it doesn't really depend on copper. It only depends on the duality of copper. So this factors through Grothendieck Witt of C, and let me write copper duality S. So that's sort of the quadratic functor I obtained by taking the bilinear part, evaluating on the diagonal, and taking C2 fixed points. And then this is sort of the terminal copper that still maps to the correct K theory. So I have this factorization, and from that perspective, somehow it's weird to ask that all of them are 2-adic equivalences. It's just not the right thing. So stop asking this, and instead ask that only. sort of unreasonable to believe that any linear perturbation that deviates from the terminal thing that still maps to fixed points on K-theory should also be an equivalence, unless you happen to prove something about this map. Okay, so that sounds like bad news, but really it's not. So corollary of what we've seen last time, so maybe you're sad for a moment, but a corollary of last time is that if you do this, okay, we'll maybe be led into, you know, divide and conquer. Maybe we'll address this problem in a moment, but for sure, if we're interested in that particular guy, for instance, these genuine symmetric things that I told you something about, I better have to understand this map. Yes, there's no way around it. And so the statement is, I need to understand the failure of this map to be an isomorphism, but I am in luck because I can compare to L theory. I mean, this I'm allowed to do. And the statement is that this map is a pullback. Yes, why is that? Because the fiber terms are given by K-theory and C2 orbits, but again, the K-theory only sees the duality. So on the duality, these two things are the same, and so I'm allowed to calculate the difference between the Grothendieck Witt theories I care about in terms of L theory, and now I just demand for you to accept that I'll indicate some steps today that say that this is a much more reasonable object to calculate relative terms of. In fact, now we even have explicit formulas for the fiber. Sort of an extension of work of Michael Weiss and Bruce Williams in this Poincare world that I've learned from Jonathan Hapas. But for what I want to explain today, sort of a pedestrian approach will suffice. But sort of this relative term is understandable because it's sort of L-theoretic in nature, and L-theory is easy. As we have explicit descriptions for any homotopy element, and so we can try to just maneuver ourselves around by hand. And that's.
If that map wasn't equivalent, then you sort of have to take the L-theory completely out of the picture.
Say again what?
The map would be not an equivalence. If that was an equivalent, you sort of taking the L-theory out of the picture, right? You'd say that
if that map were an equivalence,
determine the Grothendieck theory just from the equivariant homotopic type of the K-theory.
yes, that would be.
That is a little bit.
That would be. Yes.
The L-theory was not there.
Yes.
And this is saying it is still there, but.
Yeah, I don't think it says it's not there. It just says that it doesn't contribute in an interesting way, and that's.
From the equivariant homotopic type of the K-theory picture, right? If it was an equivalent. Yes. There's no L-theory on the right-hand side.
I think the statement is if that map is an equivalence, then L theory is just Tate of K theory. That can or cannot be true. And but the statement is L theory would be determined by this, of course, and that might or might not be true. But again, maybe what you're trying to get at is also that this idea that we shouldn't ask about each of these maps being isomorphism. Sort of, there's a terminal one, and then instead we compare to that. That's sort of the more reasonable thing to do.
Grothendieck Witt has two parts to it, right? There's a K-theory and an L-theory.
That's correct.
Right? And this would sort of, if that was an equivalent, would sort of take the L-theory out of the picture. No?
I think you can say it like this, yes. It would say that it's determined by a purely K-theoretic piece. But it turns out that this is true in a number of cases, and so I'm not willing to say that that's not an okay situation to be in. It's just okay that the yeah.
Sort of allow us to reformulate L-theory in terms of K-theory, right?
Yes, that is correct and surprising, but it just turns out to be correct sometimes. Yes, what can we say? Yes, sometimes it's true. All right, this is the first statement I wanted to make. So we have to sort of separate variables, instead try to understand something about this homotopy symmetric structure. That compares hopefully well to fixed points on K-theory, and there's a second step that says this. So let me summarize a theorem that says something to these effects. So that's now proven in the third of the series of papers, where we actually get sort of to the juice of the calculations for actual rings. So let me phrase it in the following way. So let R be a ring of integers in a number field. e.g. r is equal to z. But it could also be a localization. You just take your favorite number field, take the ring of integers, and localize at some elements. That's still fine. Technically speaking, any Dedekind ring is good, for now at least. So then there are two statements you can make. First is that the map from Grothendieck Witt of perf R with, say, the copper epsilon genuine symmetric. Oh no, maybe here I want to put the quadratic thing. So that maps to GW perf R copper epsilon symmetric R. So this is exactly this comparison map that I'm indicating here. The left-hand side is the one I might care about, having to do with actual quadratic forms. The right-hand side is the thing that possibly compares well to K-theory. So this map is, okay, let me put it like this. So I have once this map, and once I have the map for the epsilon genuine symmetric structure. And here I have the same term. So this statement is this map is an isomorphism once I take its connective cover. It's an isomorphism on all homotopy groups in degree 0 and above. And this map is an iso on pi star for star. Okay, now maybe maybe 1 if epsilon is 1, or maybe 2, no 2, and star greater equals to 4 if epsilon is minus 1. Okay, so what I want to say is that this map, okay, this map is an isomorphism on connective covers, so that does everything we want. This map is not quite an isomorphism on connective covers, but the fiber has extremely few homotopy groups only. They're like in degree 1 or maybe 1, 2, 3 or something like that. Yes, a very low amount of homotopy groups that prevent this map from being an equivalence. Okay, so that's a matter of fact. So let me continue with statements, and then we see where we go. The second statement is that I can look at GW of perf R with the symmetric structure. And in some sense, here I explain to you from the perspective of a ring of integers in a number field, I understand these terms as good as I can once I understand this. Okay, so from now on I care about this. This term I can compare to GW of perf R, where I've inverted 2 in the ring R. And that sounds maybe like, I don't know, something special to do, but I'll indicate later what happens, or why this is interesting. So this is a 2 local equivalence on pi star for star greater equals to 1. It's an injection on pi 0 in general, and on positive homotopy groups it's an isomorphism. And I include this mainly as to say in the beginning I said something to the effect, well, if you have a ring in which 2 is invertible, all these different Poincare structures agree, and many things were known, and so this statement tells you that if you're interested in 2 local Grothendieck Witt theory of like genuine epsilon symmetric Grothendieck Witt theory of a ring of integers in number fields, by that result you reduce to the homotopy theoretic guy, and by that result you're freely allowed to invert 2 in the ring, and you can just appeal to all the things that are known already, if you want. So we do this in the paper to prove the following extension of this result. Shows that if you do this guy, and you ask about this comparison map of Thomasson's, say, that this map is an equivalence. Okay, so B features in the proof of C, and one way you can do it, you sort of, I'll explain to you how to roughly do it, is by reducing to the case where 2 is invertible, and then you cite from the literature that it's true. So today I only want to discuss the case where R is the integers, in which case we'll just prove this sort of this thing by hand. I will not have to appeal to sort of the general literature, which involves some rather serious stable motivic involves stable motivic homotopy theory, at least the current proofs. So if use some technology that's a bit overkill for just the fact of the integers that we maybe want to use. That's a 2-adic equivalence, thanks. Yeah, it's not a non-2-adic equivalence. Yeah, I mean, actually it's an equivalence if and only if R is totally imaginary, I think. Once R has a real embedding, it's incorrect. Yes, once the number field that you look at has a real embedding, it's incorrect integrally. And if the number field is totally imaginary, then it's integrally correct. Okay, good. Is that... can you say again? It's an S. The actual Q, there is a version of it, but it's not correct. Well, it's not correct. Yeah, so it turns out that if you have a ring where 2 is invertible, then it doesn't matter if you do quadratic or symmetric forms because anything is uniquely polarized. So here on this side you don't see a difference, and then on this side you do see a difference in general. And so the Q version is incorrect. You cannot do this. This is specific to the symmetric case. The genuine quadratic thing, which is closer to what one sort of wants to calculate in practice, is close to being correct by that result, but not quite, as there's some 2 torsion minor terms that I'll indicate later. Okay, so there it's not far off. Here it would be a 2 local equivalents for the genuine quadratic guy, one's pi star, star is big enough, whatever these numbers tell you. Okay, so what are the ingredients? I quickly want to say something. I mean, for A, it's some explicit computation using algebraic surgery. So let me tell you in words that this corollary tells me that in order to prove this result, I can freely replace GW by L. Yes, now I need to prove that a map on L theory is an isomorphism in a certain range of degrees on homotopy. So I show surjectivity and injectivity by hand. And then every element is represented by a Poincare complex, by a Poincare object with respect to the correct form, blah, blah. And every relation, every cobordism is also represented by an actual cobordism. Yes? So both surjectivity and injectivity tell me something about I have to lift Poincare objects with respect to this kappa S, epsilon S structure to the genuine quadratic or the genuine symmetric thing. And now the sort of computational fact is that the L groups of these genuine quadratic and genuine symmetric structures can be described not as thinking about, you know, the underlying Poincare objects being just the same types of objects, just perfect complexes with a different type of form on it, but you can reinterpret the situation as saying it's the same type of form you have to look at. It's like homotopy symmetric forms, but on very specific objects. Yes, and the objects are specific in the sense that they satisfy certain connectivity ranges. You have to make your complexes sit in a certain range of degrees, and in this range of degrees, this kind of structure and this kind of structure just happens to be the same datum. So really, you can rephrase the statement about making objects sort of be concentrated in a certain range of degrees, and this is something that algebraic surgery is there to do. And so the ingredients that go into doing this kind of surgery is the fact that this ring of integers is a ring that has global dimension 1. So it's a homological condition that allows you to do these things. I'm happy to explain this in the exercises or whenever anyone is interested. I think it's just too specific of a computation to perform here now. But what I want to stress is that the fact that these numbers are so low, that this is an isomorphism for star greater or equals to 0, and 2 and 4, they have to do with the fact that the number 1, which is the dimension of such a ring, is also very small. If you have a large dimensional ring, a variant of this is still correct where you adjust the numbers correctly. Okay? The numbers just get higher. Okay, so that's a computation. Now let me say something about B, because it will feature in sort of the computations later anyhow. Well, I already sort of told you what you have to do to prove something like this. I think. So one of the examples of typically non-split Verdier sequences, or PV sequences, were exactly those. I said take a ring, take your favorite set of elements, invert them, and then you can, well, look at perfect complexes over R, perfect complexes over the inverted ring, and then the fiber term will just be the torsion modules. Yeah, so that's what I call perf R on S. And so now S is 2, so it's perf R on 2. And it's just the restricted copper. Yes, so this is a PV sequence. And as a result of localization properties for K theory and for L theory, we deduced that GW sends this to a fiber sequence. Yes? Okay, so understanding the fact that this map is too locally an isomorphism on positive homotopy says something like this guy too locally has homotopy concentrated in degrees less or equal 0. Or less or equal -1, I don't know, so less or equal some number that's correct for this statement to be true. Okay, that sounds good, but now, I don't know, how do you access the two torsion perfect complexes over R? In K-theory, what one does is you observe that they have very specific generators. And so let me say it like this. So assume you pick a prime ideal in R, which lies over 2. So it contains 2, I guess. That means then I can look at an inclusion map from R modulo P to two torsion R modules. Yes, if I have an R mod P module, I just think of it as an R module, and then I observe it dies when I invert 2 because the prime was over 2. So any of these guys ought to give me a functor from here to here. And in K-theory, it's a Devisage theorem of equivalence that says this is a good functor. This is a functor that induces something like the inclusion of a direct summit in K-theory or so. So this is a good functor to look at. And now we need to upgrade a statement of this kind to Grothendieck Witt theory. So that means I have to write down some duality here, at least in order, to have something reasonably to compare. And then I observe, well, like my favorite element in here is R modulo P itself. So that goes to R modulo P here, because I just said think of it as an R module. Now if I dualize R modulo P, what happens? Well, P is a projective module, because R is a one-dimensional ring. And so somehow the map from P to R is a one-step resolution by projectives. Now if I dualize this, I see that sort of, I get a shift in the duality somehow that you think is going on. So what I have to do is I have to put omega of kappa as R in here in order to have a chance to have a functor being compatible with the dualities. Yes, this omega being exactly omega 1 is exactly the fact that R is one-dimensional. Yes, this is the dimension of the ring that you're seeing. Okay, so you can do this, and then you can take the sum over all such P in spec R over 2. And you have a map like this. And then the theorem you want to prove is that this is a GW isomorphism. Yes, that would be good. Then we reduce things to things like R modulo primes. And because I've started with a ring of integers in a number field, then R modulo P will be some finite extension of a finite field. This sounds like a finite field. We'll be hopefully able to calculate something by hand. Okay, so how can we possibly prove that this is a GW isomorphism? Well, I do yet again the fiber sequence, say, well, it reduces to a K-theoretic statement and an L-theoretic statement. Okay, so the K-theory part, this is fine. That's sort of Quillen's Devisage theorem. And in L-theory, the statement is that, so in this explicit computations doing algebraic surgery, one can set up a general theory of performing these algebraic surgeries, and the only thing we sort of used in that case is the concept of a T-structure. So in this case, I sort of use a T-structure on the category of perfect R complexes. And the statement is that in that world of a stable category with a T-structure that plays well with the duality, you can perform certain kinds of surgeries. And that argument can just be used to access this category of perfect modules that vanish if you invert 2. Yeah, the T-structure just restricts. And what will just come out to be true is, again, using algebraic surgery methods, is that you reduce the statement you care about in L-theory, sort of, again, via algebraic surgery. The statement you want to prove reduces to a Devisage theorem for symmetric Witt groups of abelian categories. And then you open up old books, and Knebusch and collaborators, Knebusch et al., tell you you're good. Yeah, so Knebusch and collaborators that I forgot, I apologize, sort of in the 70s, essentially, studied symmetric Witt groups of abelian categories. Just look up what they do, and they tell you this is you're fine. Okay, so this tells us that this is an equivalence. So Grothendieck-Witt theory will give me a long exact sequence or a fiber sequence, and this is a finite direct sum. So Grothendieck-Witt theory will commute with finite direct sums. So it's really a statement. I've reduced myself to understanding GW of this guy. GW of this needs to be, I don't know, small. Yes, small in the sense no positive homotopy or something. Okay, so let's try to work out why that is. Maybe I can do this here. So why is that? Well, let's try to calculate GW of a finite field of characteristic 2. Yes, all of these R-mod peels are finite fields of characteristic 2. And here I'll run the game backwards again. I'll just try to compute this and write it as FQ epsilon s HC2. It's a legal move I think I'm allowed to do. I can study this map. And this map is an equivalence if and only if, well, another map is an equivalence which is adjacent to it in a pullback diagram. And what is adjacent to it in a pullback diagram is if I look at L theory of this guy and K theory of this guy, and I have to put Tate C2, right? This is a pullback, so I can equally well study this map. Okay, and now there are two things I can do. First, I calculate both sides. So calculate both sides. Okay, again, I use algebraic surgery to say that symmetric L theory of a field, fields are even zero dimensional, the surgery works even better. These are concentrated in degrees divisible by 2. They're 2 periodic because we're in characteristic 2. So symmetric and anti-symmetric forms agree. That's essentially the reason why this is 2 periodic. And they won't have anything in negative, in odd degrees, yes? And in even degrees, it will just be 2 periodic on the symmetric Witt group of this field, FQ. So this is what the homotopy is on this side. And on this side, one can use this. So there's some fact that tells me that this is equivalent, or maybe I can do it like this. So the K theory of finite fields has been calculated by Quillen. And the only interesting homotopy group that appears in which 2 is not invertible is pi 0. It's the only group on which sort of 2 doesn't act invertibly. Yes, the other homotopy groups of finite fields are prime to Q torsion. So when I take Tate of something where that's prime to 2 torsion, that just is killed, and so I'm allowed to replace this guy by that, and I have to take Tate C2, but I have to remember what the involution is, and if you work out this omega thing, omega on K theory acts as a sign, so it's maybe not so surprising to see that this is the Tate construction for the minus sign coming out. Okay, so both look correct in the sense that the L theory, if I forget about this omega, or if I forget about the omega here, in which case I get this, it's just a Z mod 2 sitting inside even degrees. So I've used here that the Witt group of a finite field of characteristic 2 is just given by F2 via the rank mod 2. It's some classical computations. So you know abstractly they look the same. And then you can do different things. You can either calculate explicitly what the map does, or my favorite trick, and we'll use this many, many times. So we use, so get rid of omega, right? Showing that this map is an isomorphism on the homotopy groups is the same as pulling the omega out. And then it's the same as forgetting about the omega because, yes, so I'm allowed to leave this away. And then the L theory of FQ, kappa epsilon S, to K theory of FQ, kappa epsilon S Tate C2, is a ring map. I haven't said anything about this. This is not really strictly speaking necessary, but it's very convenient. So the fact is, over a commutative ring, you can take the tensor product of forms, and that makes everything sort of multiplicative objects, and all the maps are multiplicative. You just have to believe me. It's maybe not so super surprising. But then let's observe what is this. I mean, this ring map on homotopy, it's F2 adjoint T plus minus, where T has degree 2. And this is the same ring, abstractly. Yes, and that's an exercise to check what are the ring maps from here to here, and there's only one. It's the identity. It's an isomorphism. Any ring map is an isomorphism because I have to send T somewhere. Everything is determined by where I send T, and it has to go to unit, so I cannot send it to 0. But there's only one other element I can send it to, it's T. So I'm done, okay? So this is good. So for finite fields, we sort of get the fact that this is an isomorphism for free because you just use multiplicativity here. So then you get that this guy is the fixed points on that, but that is still equivalent to z minus hc2. Yeah. Sort of it's still something in degree 0, and then you take cohomology of that sits in negative degrees. So that also sits in negative degrees. That's true for any such prime that you've chosen, and so all of these terms sit in negative degrees, and hence this is an iso in positive degrees. That's roughly the computation you can do here. Yeah, the statement is that this map is an equivalence, and this guy is equivalent to just z acted upon by hc2 taking fixed points, and that sits in negative degrees. In strictly negative degrees. Here you have h, that's right. I used the Tate trick to use multiplicativity, and then it tells me everything. But see that this is an exact instance of the kind where if I put on the right-hand side K-theory with orbits, then the same argument is still true. I still only see the z and the orbits acting on it. So there I pile up all the z mod 2s on the group homology of C2. And in the L theory, I also have all these z mod 2s, and they cancel out. And a slick way of seeing that they cancel out is instead to compare L theory to Tate and use multiplicativity somehow. It's just the better thing to do. And this tells you that this guy is very small. Sort of all the torsion you see in both L theory and the orbits of C2, of this group homology, they cancel out. Okay, so this is a calculation you get. And you get slightly more from this. I've proven to you that sort of the homotopy limit comparison map on all of these terms is an equivalence. Yes? So if I want to show that the homotopy limit map is an equivalence also here, I reduce it to this case by that trick. And now I am allowed to cite the literature. You open your favorite books or papers on motivic homotopy theory and this question, and they will tell you, I don't know, if you have a scheme in which 2 is invertible and all residue fields have mod 2 finite virtual cohomological étale cohomological dimension, then you're good. Okay, but I don't know. Let's just have a little bit more fun in calculating things for z adjoint 1 over 2 by hand. So I don't know, it's more fun. But I mean, at that point, we're sort of done with a proof of C. Because I just tell you, I mean, here you look up the literature, people have already done it for you, then I can just cite it. But maybe it's not so helpful. But I just wanted to indicate sort of what you can do for the case of the integers by hand. So for r equals to z, now we'll indicate that k of z, oh wait, I should say gw of z adjoint 1 over 2 to k of z adjoint 1 over 2. Maybe I should put the epsilon symmetric guy in here. HC2 is a two-adic equivalence. Yes, and then I know that the GW of Z that I care about is sort of pi0 injective in that, and on positive homotopy groups in isomorphism. So for all practical purposes, this is sort of the thing I actually need to calculate. And so here's a theorem of, I guess this was first suggested by Böckstedt and then proved by Rockness and Weibel, is that we understand K-theory of Z adjoint 1 over 2 at prime 2 relatively well. Yes, so this is a question about a two-adic equivalence. So I'm freely allowed to two-adically complete everything on the inside. And the statement is that K of Z adjoint 1 over 2, I can do a number of things. So I can map this ring to the reals. Then I get a map to the algebraic K-theory of the real numbers. That's some group completion of modules over R. And I can remember that R comes with a canonical topology. And I get a canonical map to KO. Okay. And there's another thing I can do. I can map to the 3 adic integers. So these are the 3 adic integers. And you are allowed to think about them as sort of something that projects to K-theory of F3. And two-adically, this map is an equivalence. That's a result of, I guess, maybe, I don't know, who's this? Let me say Gabber or so. I don't know, it's a fact that this map is an equivalence. And then you can do something super stupid. So Z3, you can embed into C3. So that's some non-Archimedean weird field. And that field is isomorphic as a field to the complex numbers. So that just means, in effect, there is a ring map from the 3 adic integers into the complex numbers. Choose any such map. You get a map from here to K of algebraic K-theory of C, and then you do the same topological blah argument to get a map like this. And then surely this diagram will commute because everything is induced by maps of rings. And I mean, a map, there's only one ring map out of Z adjoint 1/2 into any ring in which 2 is invertible, yes, because Z is the initial ring. Yes, so there's nothing to check. This diagram commutes. It's a commutative diagram of rings, of commutative rings. And so even this diagram is a commutative diagram. So this is a commutative diagram of spectra with C2 action. Yes, I have to care about these C2 actions in a moment. I made a choice. It commutes. For any such choice, it commutes. What can I say? It's correct. Yeah. Yes. No, but you are absolutely right. I made a choice. And sort of figuring out the dependencies of these choices has caused a lot of emotional harm to myself. So. Yes. So okay. So this is a matter of fact, and the theorem is this map. This diagram is a pullback. Okay. That's the theorem, and it's equivariant. And so let me just say on this side, the C2 action is just the one that we have. On this side, it's just the one we sort of algebraically always see. Let me tell you what it corresponds to on this side. Here, it corresponds to the trivial action. And why is that? Well, it comes from the functor that sends a module to its dual. But over the real numbers, I can choose a positive definite form, a scalar product, and that identifies the dual with the usual thing. So that trivializes this action. What happens over the complex numbers? It's still induced by sending a C vector space to its dual, and now choosing a Hermitian form, the dual vector space is isomorphic to the complex conjugate vector space. So here, the involution that comes out is the complex conjugation action. Yes? So much we know. And okay, so then this is a good thing to start with. So here's a proposition that tells you the L-theoretic side of the story, and it just says literally the same. You take L-theory of Z adjoint 1/2, L-theory of the reals, L-theory of the complex numbers, L-theory of Z3, and the statement is this is also a pullback. So the left-hand side is a difficult theorem to prove, the right-hand side is not a difficult theorem to prove. So here the proof is roughly you calculate all terms. And again, it's not difficult to calculate all terms because everything is turns out to be 4 periodic, because all of these rings are so easy, everything is just 4 periodic, and the only groups that you see are Witt groups of these rings. Okay, now you open up your favorite book about symmetric bilinear forms, and they're Witt groups, and you just check what these things are, and there's a small calculation you have to do that says something to the effect that this map is interesting enough. So what I'm trying to say is that all of these guys have homotopy concentrated in degree 0. So there will, this guy is a pullback diagram if and only if the map from pi 0 of that to the pullback of the pi 0s is an isomorphism. That's a purely algebraic question you have to resolve. And yes, if you're around for the exercise sessions, I suggest that we work out this computation. It's great fun. There's a little bit you have to do, but it's more or less explicit. You just write down forms that represent the correct elements, you do the computation. It's good fun. All right, so from here, to see that Grothendieck Witt of Z adjoint 1/2 to K of Z adjoint 1/2, HC2 is a two-adic equivalence. I again play the same trick and say I replace everything by Z adjoint 1/2 and Tate. Yes, so I do the L-theoretic thing with Tate, but now I have these two pullback diagrams, so you reduce the same question for Z adjoint 1/2 to Z3, R, and C. So this reduces the case, reduces this question to the case of Z3, the reals, and the complex numbers. Yes, because if, I have a commutative diagram by applying Tate here, this diagram maps to Tate of that diagram. If it's an iso in 3 of the terms, it's also an iso on the 4th term. Huh? All right, so this is the thing you have to do. And then, this is maybe a more serious exercise, but it's something I won't go through now. So let me call R either, or let me call E either L theory or Tate of K theory. And then the statement is that if you evaluate this functor on Z3, what you'll get is Z4 adjoint B plus minus 1. If you evaluate it on the reals, then you get, what do you get? A Z adjoint B plus minus 1. And if you evaluate it on the complex numbers, you get Z mod 2. And in each of these cases, B is sort of the same B and it has degree 4. It's sort of some dummy variable that sees that everything is 4 periodic by a specific element that lives beneath all of these rings. And okay, oh sorry. So here, maybe I two-adically complete everything, and so I do that. Yes, I mean, or maybe it's better to do that. So then it's correct. So this is. Now it's correct. So I look at the function that is L theory two-adically completed, or Tate of K theory that turns out to already be two-adically complete. And the question whether or not the map from here to here is a two-adic equivalence is the same as asking whether or not the map between these two functions is an isomorphism, and those are the values. And now you do the same exercise. Same argument as before. Any of these rings, any self-map is a self-isomorphism. Again, by periodicity. I mean, there is just no way of mapping this ring to itself without it being an isomorphism. There's no way of mapping this ring to itself without it being an isomorphism. It's just a fact. Okay, so that's fine. So that means check. Sort of. Now we win, and Grothendieck Witt of Z adjoint 1 over 2 is in fact equivalent to K theory of Z adjoint 1 over 2 HC2. But now I told you what is K theory of Z adjoint 1 over 2. I just know what it is. Here it is. So I can calculate what HC2 is. Yes? So let's just do that. Let's see what it is. So the consequence, Grothendieck Witt, yes, epsilon symmetric of Z adjoint 1 over 2, sits inside a pullback of the following kind: KO HC2, KU HC2, and K of Z3 HC2. Okay, now there is one thing I should have told you, which is not obvious from the diagram, but it turns out it's a computational fact, complex conjugation, that you understand this map very well. It's not some arbitrary map. It turns out to be the transfer in a fiber sequence that you can write down, and it's the fiber of a specific map. It's called psi3 minus 1. So what just is true is that the K theory of Z3 completed at prime 2 is given by the fixed point, so to say, of the psi3 Adams operation acting on Ku. Okay, so not only do I understand this map abstractly, it's given in terms of Adams operations. And so that just means that here it's also true that it's given in terms of Adams operations. Sort of, it's still psi3 minus 1. Yes, that has to do with the fact that this complex conjugation action is secretly psi minus 1. And any two Adams operations commute with each other. So this psi minus 1, in fact, if you take psi minus 1 fixed points, you just get Adams operation on psi okay. Also, what comes out is that okay. So now we open our books in equivariant homotopy theory, and our friends have calculated everything for us there. So what is the complex conjugation fixed points of Ku? That's Ko. Now we're working with this connective thing, but imagine you map this to the periodic eye, then the fiber is something co-connected. If I apply fixed points, it remains co-connective. So through the eyes of spaces, this is roughly Ko. I mean, this is sort of omega infinity equivalent, surely, to it. Yes. Yeah. So this looks like Ko because the C2 fixed points on periodic Ku is periodic Ko. And what is it? The Atiyah-Siegel completion theorem essentially tells us that up to 2 completion, this is 2 copies of Ko. As the C2 fixed points, that's the cohomology of BC2 acting on Ko. That's up to 2 completion, just the C2 equivariant real K theory, and that's 2 copies of K theory. Okay, so we have these maps, and under this equivalence, this is still just psi3 minus 1. So that gives you somewhat of an explicit description of that term, of this term, in terms of a fiber of the map from Ko to Ko with psi3 minus 1. And now I'm lying a little bit here because I was being uncareful about exact connective cover. So let me do the move that Manuel also made and say I'm not discussing pi0, pi1 issues. There are some pi0, pi1 issues that you resolve in the way such that the theorem I'm going to write down is correct. Okay. The Grothendieck trick, yes. Yes. And actually, let me also say this. So here's something extremely convenient. You observe that this map, oops, so this map, I apologize for, so there's a map from KOHC2 to KO, KUHC2 to KO. That's 2 copies of KO. And what comes out is that this map is the diagonal, the co-diagonal. It's the fold map. It's the thing that's the identity on both of these copies. Is that correct? I surely hope so. Well, okay, in any case. So what you see is that because this is a pullback up to pi0 issues that we Grothendieck don't care about, there is a KO mapping in, and don't worry that you cannot read it. And this KO mapping in fact, splits. Because I can map to here and just project away one of the 2 factors. And the statement is that if you work with Z, then this is in fact only like pi0 injective in this situation. And this map from KO in fact does not factor through GW of Z. That makes things slightly annoying to state for exactly such. Let me not go through it here, but sort of in the Z adjoint 1/2 business, everything is clean and nice. In the Z case, you have to tweak around a little bit what happens exactly. But okay, let me do a consequence or 2 consequences of this computation, essentially. And the theorem we had before saying that this is essentially GW. And let me also do a correction that says that this is really only the epsilon equals to 1 case. And then the epsilon equals -1 case, the involutions come out a little bit differently. And I have to give you a different formula, but the spirit of the argument is the same, so let me just write down what comes out. So I think, yeah, I don't know. Okay, let me just say this is as follows. So we get that, for instance, the space underlying the symmetric Grothendieck Witt theory two-adically is going to be given by omega infinity 0, so I take the unit component of the spectrum I'm about to write down, and the spectrum is just given by KO plus the fiber of psi3 minus 1, thought of as a map from KO to tau greater equals to 2 KO. Yeah, so this is what comes out if you do the correct pi0 things. So this is you have omega infinity 0 of the quadratic guy, which, remember, is secretly sort of this perf Z stuff with the genuine quadratic structure, which compares to the symmetric thing, at least in a range of degrees that error terms you only expect to happen in like maybe pi1 or so. So we can still access it quite well, and it comes out to be KO plus fiber of psi3 minus 1 from KO to tau greater equals to 4 KO. And let me mention that I really mean what I write once in my life. So here, I guess one can upgrade this to somewhat of a statement that is still true. Sort of as a connective spectrum, but I already told you that this KO doesn't really map into it. So there's some pi0 issue going on here, but there's still a spectral statement you can make. In this situation, I've in fact really worked in spaces, and I've spectrally, there's a map of spaces of which I can choose sort of an untwisting as spaces, but not as spectra. Yeah, so here already something slightly more subtle is going on. I've simplified the space in a way that I'm not allowed to simplify the spectrum. That comes out. Let me do the minus symmetric guy, so the symplectic group things.
What is the statement is as?
As spaces. Equality as spaces. So in the infinity category spaces, there's an equivalence of this kind. And then one can upgrade some of the statements to better statements, and I won't do any of those here. Yeah, for the purpose of what I want to discuss, or what I want to sort of hint at, this will be perfectly sufficient. Yes, so here you'll get something like omega infinity 0, and it's just one single term. It's the fiber of psi3 minus 1, now thought of as a map from KU to, I guess, the connected cover of KSP. So KSP is sort of a fourfold shift of KO, but then, or the K theory of quaternionic vector spaces, so to say. And this comes essentially from the fact that, here think about, we had something like KU, what is it we had here? No, here we had KR, but with minus forms. So here we're talking somehow about real symplectic forms, and here we're talking about complex antisymmetric forms, and they just turn out to have like topologically the homotopy type of the unitary group and the symplectic group. This is why these things come out. It's just okay. And sort of the most fun guy, or the most complicated one, is the skew quadratic case, and that looks like B z mod 4z times the fiber of a map from the symmetric guy, the minus symmetric guy, minus, and then there is a map to kz mod 2,2 times kz mod 2,3. Yeah, so there are two explicit cohomology classes in this space. So omega infinity, I should have said, sorry. So there are two explicit cohomology classes in the space that I have to kill. So I take the fiber and then I take a product with the classifying space of z mod 4. Take the product of all these things, this is what this space comes out to be. Okay? Alrighty, so this is just what it is. And from here, it's sort of, I mean, a combination of opening up the books about what are the cohomologies of all these spaces to calculate the cohomology of these spaces. I mean, just calculate the cohomology, the F2 cohomology, say, from this presentation. Or you open up the books, written again in the 70s or so, that tell you what is the cohomology of, you know, KSP, what is the cohomology of, I don't know, a BO, I guess we all know, BSO, B-spin, all these kinds of terms we just have to look up. And then we have to evaluate some spectral sequences that involve this Adams operation on it, yeah. Just run this spectral sequence. So let me just tell you two of the cases of how things play out. Somehow, these are the easiest ones, so those I let you do yourself, if you want, or at least try to do yourself. This is sort of about the cohomology of BO and sort of Adams operations acting on BO, so you have to look up how do Adams operation act on Stiefel-Whitney classes or so, but I claim you can just look it up. So here are two consequences of this fact. So maybe I should say this, I'm currently writing up with Fabian and Thomas. For instance, you get that the cohomology of the infinite symplectic group over the integers with F2 coefficients can be described. And why is that? Okay, this is a homological stability result. So this symplectic group, the stable guy calculates turns out the stable homology of the group completion of antisymmetric forms. Now I told you the group completion of antisymmetric forms is this genuine minus S GW, but the genuine minus S of Z is the same as the symmetric one because of this dimension 1 business. And that's the same thing as some fixed point business. So I mean, those are the things I'll just have to write. Look at what happens here. So here I'll just have to calculate what comes out. And you'll see it's a polynomial ring on things that are called CI. I think, what is it? I wrote it up, yes. I is greater or equal to 1 times a polynomial ring on classes BI. How do I, yes. I also greater or equals to 1, and the degree of CI is 2i, as you would imagine, and BI is 4i minus 1. So once I've done this, I can give these elements a name, and it's called C1 and B1. So now I've made more specific what this other term is. And now a similar argument as here with this group completion business tells you that the cohomology of the quadratic symplectic group, I mean, I apologize for the chalk. I don't know what to do about it. There, just take better chalk is the statement. Yeah, okay. So this is the group. It's given by the union of all the symplectic groups. So those are the isometries of the form of like WGs. These usual manifolds, you know, in the correct dimensions. And this form, this antisymmetric hyperbolic form, comes with what's called the ARF invariant zero quadratic refinement. And you can look at the subgroup of all those isometries that preserve this quadratic refinement. And this group, this stable cohomology will be computed by the group completion of the minus genuine quadratic guy, so this quadratic thing. Yes, and then we look up what is it? Well, it's apparently it's this guy. So I have to calculate what this is. And here the Serre spectral sequence becomes funny. So in all of these three cases, the statement is the Serre spectral sequence involved in any of these computations collapses at E2. in this case, it collapses at E4. I've never had that in my life, so that's kind of a first for me. So it collapses at E4, and what comes out is the following. I mean, just to get an impression of what are the kind of things that come out. It's a U and an X and a ZJ and a CI. The I is, I guess, greater equals to 2. The J is greater equals to 1. Tensor then, this is an exterior algebra and not a polynomial algebra. And here I get classes that are called V, Y, and BI, and then I is again greater equals to 2. Okay, and maybe I'll write down what the degrees are just so that we see what's going on. I guess this is degree 2, this is degree 1. So these come from the BZ mod 4. And then the degree of the ZJ are 2 to the J plus 1, I think. Or minus 1. No, plus 1. Then the degree of the CI are still 2i. The degree of the BI are still 4i minus 1. And is any element missing? Yes, X has degree 4, and Y has degree 5. Yeah, something comes out, but it's explicit. And let me tell you that at least it was conjectured that these things should be so. So this is something that Berwick and Karoubi sort of conjectured. In the symmetric case, they thought what should come out is the same thing as that what happens for Z adjoint 1 over 2, and for Z adjoint 1 over 2, I haven't really done anything new. I just cited that one knew these things already. Really, our contribution is to say that for Z, the same thing happens. I believe in the quadratic case, there was no conjecture made. Nobody really knew what it could be, and it's quite surprising, at least to me, that that on the level of these quadratic groups, the difference to the symmetric I is so small. And it's really related very, very specifically to this fact that the integers have dimension 1. Only that is sort of the reason for the algebraic surgery to tell us that we understand the difference well enough to make these computations. So if you replace sort of Z by some like 5-dimensional ring, all of a sudden you'll have spaces appearing here that might be much more complicated than these easy products of Eilenberg-MacLane spaces, and you get into all sorts of trouble. Also, I want to highlight that like these symplectic groups, for instance, they receive maps from mapping class group or from the spin mapping class group, and these cohomologies are sort of known, and it's great fun to try to understand what's going on here. So let me advertise that there's still like 10 days left to apply for a postdoc job with me, where we're trying to have some fun in this direction. So that's something you can do. Yeah, that was.
Not just trying to
Yes, have some fun in this direction. Well, I mean, I'm open to anything. Okay, so this is something you can do. Let me finish by saying one other thing that you can do that is not related to these group cohomology calculations. So again, I apologize for being fast here, but somehow the statement is, I mean, here are these explicit arithmetic groups over Z. It's known that their cohomology stabilizes. With F2 coefficients, it was just not known what it is, and here's what it is. Sort of explicit answer. And you can even use this to write down like integrally maybe the homology relatively easily until maybe degree 12 or so, and then, I don't know, the Box-Stein spectral sequence becomes a bit annoying, but I mean, you can do a lot of things I find quite fun. So here's another completely different orthogonal thing you can do. Another application. And it goes as follows. So imagine you have a manifold, and you have a map to BDiff plus of another manifold. As Manuel told us about. And imagine this guy is framed, or stably framed. Then this classifies a bundle like this. And it's a question you can ask. Let's say this has dimension 2n. Then the total space has dimension 4n. And you can ask what is the signature of E. It's an explicit question that I think is an interesting one that you can ask. It's famously known that in fiber bundles, the signature is not multiplicative. If that were so, the fact that M is stably framed tells you the signature ought to be 0. So in other words, what happens here is that you can interpret this number as the sort of qualitative failure of this signature product formula to be true. And now you can observe something that Chern, Hitzebruch, and Serre did also some time ago. Namely, you go to the isometries of the middle dimensional cohomology of n. Yes, and let me be specific, and I work with integer coefficients. It surely maps to that guy. And now I claim that the signature of EA, maybe let me call this LE, can be calculated only in terms of that. There's something like the signature of M with twist in LE. Yeah, so the statement is the signature depends only on this local system of forms I have on M that's classified by this composite. And so the signature is equal to that. That's good. And now what is it? What I wanted to say? Yes. Yes. So the statement is. What is the statement? Yes. The statement is this thing is a Bordism invariant in M. So I'm allowed to do this. Yes. Take brackets to indicate its Bordism class. So that approach gives me a map from like the 2D-dimensional framed Bordism of something like B of the isometry group of this form, Z to Z. And the claim is, how do you get this? Well, you do the following. So let me tell you how to extract this guy. I have these B isometries, and I told you that B of isometries, that's a path component in the space of Poincare objects in some category. So what I want to say is that this sort of for free gives you a map to framed Bordism of omega infinity of the Grothendieck-Witt spectrum of Z, and then I guess I have to do something like -1 to the n symmetric or so. Yes, I mean, I have to record whether or not this form is symmetric or skew-symmetric. That depends on n. But now this is sort of stable. I mean, this framed Bordism of an infinite loop space, and an argument along the lines that Andy explained to us with some unit, co-unit, blah, blah, says that there is a canonical surjection from this, a split surjection, to pi 2d of Grothendieck-Witt epsilon symmetric Z. And the epsilon is still -1 to the n, and then I can map that to pi 2d of L theory. And then that turns out by a calculation to be Z via the signature. And the statement is the composite sends this M to blah, blah, blah to this twisted signature of M by that guy. Okay? So in hindsight, I mean, what that means is just that whenever I have any situation of this kind, any bundle over a stably framed manifold with anything that still maps to B isometries, I can extract the signature out of it. And the way I can do it is I can just calculate this homomorphism. Yeah? And that tells me sort of universally valid divisibility results for signatures, and it also tells me by the fact that both of these maps are, I mean, this is sort of a group completion map, it's surjective, and this is also surjective, it tells me like the actual values. Okay, so let me finish just by writing down a theorem that tells you what are these numbers that you get, because they're fun. Just in this epsilon symmetric, in the epsilon equal to 1 case, there's also a formula for the other guys. What is the formula? The image of the signature map from pi 2d or maybe I should say, oh no, pi 2d Grothendieck-Witt epsilon symmetric Z to Z. And epsilon is 1, but I have to do 2d because else numbers will be wrong, is 2 to the d plus 1z or 2 to the d plus 2z, depending on d being 0, 1, or 3 mod 4, or d being 2 mod 4. Okay, so the numbers that you get are A, divisible by 2. I mean, it's only powers of 2 that you see. And B, they grow exponentially in the sort of half of the dimension of the base. Yeah, okay, so let me say in words only and then finish, I apologize, that if you stick to smooth manifold bundles, there's an index theoretic way you can prove this. But sort of this argument tells you that A, you don't need to do index theory if you don't want to, and B, it extends to forms, and C, it tells you that in this world of local systems of forms, this is an optimal result. You cannot do better than these. I mean, no better divisibility will be true, whereas for smooth manifold bundles, it's well known that sort of odd primes will contribute to these numbers, and sort of things are different. So that's another type of application you can do, just running this argument, knowing exactly what GW is. Okay, I'll finish here. Thank you. Yes, something like this enters in some of the places, but I think, I mean, for instance, the fact that this is just not a direct sum, this KO doesn't split off, is a pi zero issue that has nothing to do with additive or other things. For instance, this one, the BZ mod 4. Yeah, that sort of is. Yeah, the argument for that is sort of stupid. I mean, you observe that this quadratic symplectic group, it abelionizes to Z mod 4. And you just write down an element in it which has order 4. And that gives you a map from Z mod 4 to B of it. And that splits that off, but that's like super, I don't know, that has nothing to do with any G, I don't know. I don't think that's a unit thing, that's just an accident. Maybe, I don't really know, maybe it's an accident or so. It's a good question. Now, some of these splittings, yes, have to do with the fact that that I want, yeah, I think the answer is to some of these questions where you have to split on the space level to get these formulas, the answer is yes, and to some others, no. And the Z mod 4, I think, is not of that kind.